All right. Hey, everyone. This is the video for solving by graphing. In our solving by graphing, we use technology. So we're actually going to use a graphing calculator. All right. So make sure you have your notes with you. I have mine up right here. Right. The guided notes, solving quadratic equations by graphing. Make sure you have that with you. I'm going to skip this little bit up here, and we're just going to go straight down here to the practice problems. Essentially, what we mean by solving by graphing is we're going to give you basically a word problem, a context for your quadratic equation here, or quadratic here it's the equation. Sometimes it's in function notation, but we give you an equation that models something particular, and then we ask you questions about it, and we ask you to use the graph to answer the questions. That's what we mean by solving by graphing. So, anyways, we need to go to desmos.com. All right, dsmos.com, and this is what you'll encounter, and you click on graphing calculator. All right, so here we have our graphing calculator. Over here to the left, we're going to type in our equations that we get, and then we'll go from there. So here I'm just going to copy and paste. Oops. Oh, this is in a PDF, so I can't copy and paste. So I'm just going to type it in here. So we have h equals negative 16t squared plus 75t plus 2. Okay, so here's our equation. Ooh, it goes pretty high, huh? Okay, so this is it zoomed out. Over here you can zoom in and out. Plus means you're zooming in, minus means you're zooming out. Here's our equation. We'll end up zooming in and out a little bit just to get our answers. So this represents a football player kicks a football 2 feet above the ground with initial vertical velocity of 75 feet per second. The function h equals negative 16t squared plus 75t plus 2 represents the height h in feet of the football after t seconds. Find the height of the football each second after it's kicked until it hits the ground. Okay. So the x-axis here is the height, or excuse me, is the seconds, right? So as we move along our x-axis, each one of these little lines is 1 second. And it says the y-axis is how far it is above the ground. Now notice 0, 2 here. Okay, at 0 seconds, it's 2 feet above the ground. That's because the kicker kicks it at 2 feet above the ground, right? When he kicks it, it's not on the ground because he's a punter. So it starts at 2 feet above the ground. So at 0 seconds, it's 2 feet above the ground. Okay, now we got to figure out where it's at 1 second. So we're gonna come all the way up here where we can find, it's looking like it could cross here at 1 second somewhere. We're gonna click and drag. So we want 1 second. So we want 1 as the x value. We're at 0.98. Okay, there's 1, 61. So at 1 second, it's 61 feet above the ground. Okay, now let's go to 2 seconds. So I'm gonna drag my screen up. We're gonna find it at 2 seconds. I'm gonna click on the graph and drag around on the graph. Find my 2 seconds here. Oh, close. Okay, at 2 seconds, it's 88 feet above the ground. Now let's find 3 seconds. Keep going here. At 3 seconds, it's 83 feet above the ground. Let's find 4 seconds. At 4 seconds, it's 46 feet above the ground. And let's see, 5 seconds. Ooh, 5 seconds. Look, we're at negative feet, so we went below the ground. But when you kick a football, when it lands, it doesn't go under the ground, right? So there is no feet for 5 seconds, right? It hit the ground already. So we're done with part A. Now let's look at part B. Use the results from part A to estimate how many seconds the ball hit the ground. Well, it has to be between 4 and 5, right? Because we had 4 seconds, it was still in the air, but 5 seconds, it would have been below the ground. So it has to be between 4 and 5. Let's look at the graph here. It's a little bit closer to see this point right here. I just hovered over it, but just by estimating, It's a little bit closer to 5 than it is to 4. So I'm going to say 4.7, right? Because 4.7 is closer to 5 than it is to 4. Okay, and then part C says using Desmos, find the exact time the ball hits the ground. Okay, so I'm going to click on my graph and see right where it hits the ground, right where the feet, where the Y value is 0, it's 4.714 seconds. Okay, and that's part C. All right, let's look at the next one. At a Civil War reenactment, a cannonball is fired into the air with an initial vertical velocity of 128 feet per second. The release point is 6 feet above the ground. The function h equals negative 16t squared plus 128t plus 6 represents the height h in feet of the cannonball after t seconds. All right, so let's change our function now. Actually, this shouldn't say function, so it should say equation. That's my fault. It's a typo because it's not in function notation. Well, let's change it now in Desmos. So we have negative 16t squared. Oh, we already have that. So plus 128t plus 128t plus 6. Let's zoom out. Oh, wow, the cannonball goes a lot higher than what the punter kicked, which makes sense, right? Because a cannonball is using gunpowder, right? So it's a little bit more explosive than someone kicking a football. So let's see here. It says find the height of the cannonball after each second it has been shot until it hits the ground. Okay, well let's zoom in a little bit here. So at 1 second, or at 0 seconds, excuse me. Let's see, at 0 seconds, it's 6 feet off the ground. Okay, that's because the cannon itself is sitting 6 feet above the ground, right? It's on its rolly thing, right? So it's about 6 feet. That seems kind of big now that I'm thinking about it since I wrote this. I've never thought about it before. Probably should make it 3 feet instead of 6 feet, but we'll say 6 feet. We'll say it's a really big cannon, right? And it's pointing up in the air, and so it's a little bit even higher than that. So 6 feet above the ground. Okay, let's go and find 1 foot. It's gonna be way the heck up here, right? See this line right here is our 1 feet. Okay, so we're getting close. Remember, feet is the x value, right? So it's the left and right, or excuse me, feet. I'm sorry. Seconds is the x value. So it's left and right. Feet are the y value, up and down. Right, so we need to find an x value of 1. We're getting close here. Getting close. Oh, just passed it. Okay, so at 1 second, the cannonball is 118 feet above the ground at 1 second. Okay, now let's go to 2 seconds. Let's roll up a little bit here. Oh, we're past 2 seconds. Getting closer. Oh. Okay, at 2 seconds, it's 198 feet above the ground. Let's find 3 seconds here. Around here somewhere, right? Yeah. Oops. Oh, come on. There we go. At 3 seconds, it's 246 feet above the ground. 4 seconds is right here, right? It's our vertex. It's our maximum. In fact, 4 seconds is, at 4 seconds is when the cannonball starts to drop. So at 4 seconds, it's 262 feet above the ground. At 5 seconds, it's 246 feet, which is the same as 3 seconds. At 6 seconds, let's see here, it's 198 feet, which is the same as 2 seconds. How tall do you think it is at 1 second? I bet you already know. I bet you already wrote it down. At 7 seconds, yeah. 118 feet. Okay, and then at 7 seconds, what do you think it is? I bet you already know that one too. 6 feet. Okay, it's because of the shape of the parabola. Sorry, I keep looking at my face instead of looking straight at the camera. My bad. I'm using Zoom to do this, right? So I can screen share. It's because of the shape of the parabola, right? The parabola is symmetric, right? So because it's symmetric, whatever's on this side, on the right-hand side, is the same y value as what's on the left-hand side, right? And that's why they have the same y values, even though the seconds are different. Okay, so there's part A. Part B, use the results from part A to estimate when the cannonball will hit the ground. So let's just look here. We'll zoom in a little bit. Let's see. This is 5, 6, 7, 8 seconds. It's looking like it's crossing right at 8 seconds. So let's just say 8 seconds for part B. Okay, now remember the ground is at 0, right? 0 feet to the ground. And then using Desmos, find the exact time the ball hits the ground. Okay, so let's click on our graph and drag. Oh, it's not quite at 8 seconds, super, super close. In fact, to us, we probably wouldn't even be able to perceive the difference. But if you had a stopwatch or like a slow motion camera, you could figure out, and it would hit the ground at 8.047 seconds. So just a little tiny bit more than 8. All right, let's go to the next one. I like this one. I wrote this one myself. Actually, I wrote it after coming home from a drive to the, I was dropping off a friend at the Salt Lake airport, and it was super rainy, and it was around 1 o'clock in the morning. He took a red-eye flight because it was like half price, and asked me to take him to the airport. He was a roommate, and so I figured if I didn't take it into the airport, then it would be bad living together, right? Because he'd be mad at me. Anyways, it was raining really bad, and I was driving on the freeway, and there was like no one on the road, but it was raining so bad. And you guys, I don't know if you noticed here, but in Utah, they don't slope their roads very well. And so the water doesn't run off like it should. And so it just gets stagnant, and then you can't see the lines. And there was a time where I was in the very, very far right lane driving. And I passed underneath I was just driving normal. I thought I was in the lines and everything. And then I went under a bridge where it was dry and I could see lines, and I had actually 2 lanes over. I was in the middle lane, and I started in the far right lane. So I wrote this one because I can't stand how Utah does their roads. And it feels like they're like, doesn't seem like they're just rebuilding them all the time, and you'd think they'd do it right. Anyways, but it's super hard to see. Sorry about that. It's super hard to see the lines in the road, especially when it gets, you get reflective surfaces on it, like rain. So I wrote this one because I was mad. Anyways, so to keep water off the road, the surface of a public road is shaped like a parabola. The surface of the road can be modeled by y equals a negative 0.0012 x squared plus 0.041 x, where x and y are measured in feet. So x is the width of the road, y is the height of the road, or I guess you could say that even the depth. So let's type this into Desmos. So we're going to get rid of this. We're going to have y equals negative 0.0012 x. Is that what it was? Yeah, 2 zeros. X, and then we got squared. Now, sorry, I should have showed you. If you need squared, this is the square button, or you can do Shift 6, and that also will give you an exponent, but that's the squared button for you right there. And then we have plus 0.041x. Okay. Now this one's not tall at all, which makes sense, right? Because roads aren't super tall. If they were super tall, then we'd be falling off the edges, right? But it is tall enough to make it the water run down. All right, so here's our road. Find the width of the road to the nearest foot. Okay, so I made this one a little easy for you. Right, so you can see 0, 0. Right, so the height of the road is 0 and the width is 0 here. So it's one edge of the road. And we come over and we want to find where the road crosses 0 feet again, right, where it touches the ground again, where it's flat again, which is right here, 34.164. So the width of the road is 0, or 34.167 minus 0, right? We subtract these two values to find our distance. So anything minus 0 is itself. So the width of the road is 34.167 feet. Okay. Let's look here. This is a fun one. This is one I found online. A stream of water from a fire hose can be modeled by y equals negative 0.003x squared plus 0.58x plus 3, where x and y are measured in feet. A firefighter is standing 75 feet from the building and is holding the hose 3 feet above the ground. The bottom of the window of the building is 26 feet above the ground. Your friend claims the stream of water will pass through the window. Is your friend correct? Well, first of all, we got to type this in. Now, x and y are in feet. Once again, x is feet this way along the ground. Y is feet this way, up and down. All right, so let's type this in. So we got negative 0.003, correct? Yeah, plus 0.58. 0.58. And then we have plus 3. Plus 3. Okay, let's zoom out here. Okay, so this right here is a stream of a hose. Now look, notice at 0, right? So the stream of water hasn't gone any distance left and right. It's 3 feet above the ground. Okay, because we're assuming that a firefighter is holding the hose off the ground, which most people hold hoses off the ground. They don't hold it on the ground to shoot up, right? So that's why it's 3 feet above the ground when it hasn't traveled, when the stream of the water hasn't traveled any, right? So this models the stream of the water, right? This is the directional water. We want to know, would this ever pass through a building that's 26 feet high, right? So we need to figure out, does the stream of water, does it ever get up and down 26 feet? So let's click on our graph here and move along. Oh, hey, right there. Let's see, right about, ooh, so close. Oh, so close. But either way, right, it gets above 26 feet. So yeah, the stream of water will pass through a building that's 26 feet tall. You have to be standing 56 feet back with this particular stream of water, but it would pass through the building at 26 feet. In fact, it could pass through a window that was 31 feet tall. Okay. So let's see. Your friend claims the stream of water will pass through the window. Is your friend correct? They are correct, because if you look at the model of the stream of water here, it does go, eventually it gets 26 feet tall. In fact, it gets all the way up to 30 feet tall, or 31, right? So it definitely will go pass through a window that's 26 feet tall. You just have to be standing about 56 feet back. Okay, here's a good one. The fuel economy, Y in miles per gallon. So the up and down value now is the fuel economy. It's miles per gallon that you get in a car. Can be modeled by this equation here. Y equals negative 0.013x squared plus 1.25x plus 5.6, where x is the speed in miles per hour. So our left and right, x is our speed. Up and down, the Y value is our fuel economy, right? Our miles per gallon. The x left and right value is miles per hour. So part A, which speed does the car get the best fuel? And that's another typo. It's supposed to say best fuel economy. So let's type it in here. Y equals negative 0.013 x squared plus 1.25x plus 5.6. Okay, so just so you know, this right here, it's saying if my speed is 0 miles per hour, so if I'm just sitting idling, I would get 5.6 miles per gallon. But that's not true. We all know that if you sit idling, you actually get better miles per gallon because your RPMs are lower, right? And so this model is close, right? It's closer to the values up here where it works for. But as you get towards the ends of the model, it kind of tapers off and doesn't work very well. All right, just so you're aware. So at what speed does the car get the best fuel economy? So we know fuel economy is up and down, right? It's our Y value. So the best fuel economy would be the highest Y value. Well, that's our maximum, right? So we find our maximum, which is right here. So our best fuel economy is 35.6 miles per gallon, or 35.7 if you round up. And we'd have to be traveling at 48 miles per hour to get that. Okay, so at 48 miles per hour, our car that this models, the fuel economy for a car that this models, and this is actually pretty close. I did a bunch of research for this question when I wrote it on older sedans, like early 2000 sedans. It's around 48 miles per hour. Okay, it's the best fuel economy. So how fast must the car go to get a fuel economy of 0 miles per gallon? Does your answer make sense reality? Explain your reasoning. So 0 miles per gallon, right? Our Y value up and down is miles per gallon. So when the Y value is 0, well, we got one right here. I'm gonna click off this, and one right here. So here's 0 miles per gallon, here's 0 miles per gallon. So it says we'd have to be going negative 4.3 miles per hour, which doesn't make sense, but it says negative 4.3 miles per hour and 100 miles per hour. Okay, so does that make sense? No, right? None of those answers make sense because negative 4.2 or 4.3 miles per hour doesn't make sense. You can't get negative miles per hour. You can go in the opposite direction, but you're still going positive speed, right? That's why your speedometer is only from 0 to like 160 because you can't go negative speed. And then 100 miles per hour. Now, at 100 miles per hour, you're probably getting really, really bad fuel economy, right? Because your RPMs are up pretty high. But you're still getting fuel economy, right? It's saying, this graph is saying that at 100 miles per hour, you would go 0 miles per gallon. Well, that's not true. I mean, anyone that's gone even 90, down past Santaquin or even past Payson, it turns to 85. A bunch of people go 90. You're still getting fuel economy. If you go 100 miles per hour, you're not going to be just sitting still, right? Which is what 0 miles per gallon tells, that if you're going 100 miles an hour, you can only go 0 miles per gallon, which doesn't make any sense, right? So the answers don't make sense at all. And that's why I was telling you, at the ends, the model doesn't work, but here in the middle here, around here, where most people travel between 25 and 80, right? This is where it works. How fast must you be going to achieve 28 miles per gallon for your fuel economy? Hint, be ensured to include both answers. All right, so there are two answers. So what I'm going to do to help us out here, we know fuel economy is the Y value, up and down. So I want to know where Y, the fuel economy, is or equals 28. Hey, put in a graph for me. And see, it puts in the intersections for me. So I know exactly where it's getting 28 miles per gallon. I get 28 miles per gallon at 24 miles an hour and at 72 miles per hour. That's where you get 28 miles per gallon. And it kind of makes sense. A lot of times people think, oh, I'm going slower, so I'm getting better fuel economy. That's not true, right? Remember, cars, they have gears. They have gear systems. Most of them have 5, right? Some of the faster cars, or even a lot of the new cars, have 6 now. But it'll automatically change gears if you have an automatic transmission, right? When you change gears, it allows the car to run at lower RPM at higher speeds, right? And that's why your car goes, and then you can hear, right, when it shifts into a new gear. If you're in a manual transmission, you have to do that yourself, right? So in a manual transmission, if you're not paying attention, you can actually overheat your car, right, or tear up your transmission because your RPMs are too high. But in automatic, it does it for you. That's why these are actually, it actually happens twice. It actually probably happens more than twice, but this is the best model I could find. But it most likely it happens at a certain RPM and not at a certain speed, right? Because it's the rounds per minute, the revolution of your pistons, that causes you to use more gas. It's not the speed, right? Usually, if you go faster, the motor is working harder, so the pistons are going faster, so you use more gas. But depending on what gear you're in, right? Anyways, but that's according to this model, which isn't perfect, right? But according to this model, at 20 mile, you get 28 miles per gallon at 24 miles per hour and 72 miles per hour. All right, last one here. A dolphin jumps out of the water and its path in the air is modeled by the equation y equals negative 16t squared plus 26t, where x is the number of seconds that has elapsed and y is the height in feet of the dolphin. So x now, the left and right, is how many seconds have passed since the dolphin has jumped out of the water. And the y value, up and down, is the height of the dolphin, either in the water or out of the water. Okay, so let's put this equation in. We're gonna get rid of these ones, and we're gonna type in here y equals negative 16t squared plus 26t. Okay, so we're gonna have to zoom in here and drag over. Okay, so here's kind of this is a model of how high the dolphin jumps, right? So after how many seconds does the dolphin hit the water again? Well, let's click on our graph. So remember, the height, the up and down, the y value is the height of the dolphin. So here at 0 seconds, right, its nose is just coming out of the water, right? It's just about to jump out of the water at 0 seconds, right? It's right at the surface, right? Its nose is like right here at the surface of the water. Okay, and then it breaks through and it jumps up, and we want to figure out when does it go back into the water? Well, that would be at 0 feet again, right, above the water, which is at 1.625 seconds. What is the maximum height the dolphin reaches? So we want to find how tall, what's the height, the tallest that the dolphin ever gets as it jumps out. Well, we go up to the very tallest point, which is our vertex, right? Remember we talked about that quarter one? It's the vertex, it's the maximum or minimum point. Here it's a maximum. The tallest it ever gets, it jumps out of the water at about 10.6 feet. Okay, our y value. When is a dolphin 4 feet below the water? Do both of these times make sense in reality? Explain the reasoning. Okay, so we want to look at 4 feet below the water. So here, our x-axis, right, is the water line because that's at 0 feet, right? The y value is 0. So I want to go down to where it's below the water is negative 4 feet. So actually, I'm going to type in y equals negative 4 because that's where I want to know when the y value or the height of the dolphin is 4 feet below negative 4, the water, which is right there and right there. So it's at 1.767 seconds and negative 0.142 seconds. Now, one of these doesn't make sense. Negative seconds don't make sense, right? Because we can't travel back in time, right? Now, you could think of it abstractly and say, well, it's coming up, right? Right here, it's coming up to jump out of the water. So, you know, about 0.14 seconds before it jumps out of the water, it's at negative 4 feet. Okay, but if we're not looking at it abstractly, if we're just looking at it just plain, straight up, like we are right here, this doesn't make sense, right? The negative seconds. Now this one, 1.767 seconds, does make sense, right? So as we're timing, right, we click our stopwatch, and it's going. At 1.767 seconds, if I were to click it, stop the stopwatch right there, it would be 4 feet below the water. Okay, so that one does make sense. Now, like I said, there are some of you, if you think of this abstractly, right, if you're not thinking of it, if you're thinking of it as a whole, as a picture, rather than I started my stopwatch and didn't, then this could make sense. Okay, but just looking at the model, it doesn't make sense. And that's it, right? And actually, that's it for solving. You're given an equation, you graph it, and based on the graph, you just figure out, you answer questions based on real life situations. Okay, so that's it for this video. Now remember, January 15th, last day to do quarter one retakes. I will not accept them afterwards, and that's set in stone. Okay, so you got 2 weeks to do this to get quarter one done. Now remember, you need to watch the videos before I can help you with anything, because I can't reteach you everything from quarter one in 2 weeks. So you're gonna have to do your part first. You're gonna have to watch the videos and then write down specific questions you have, so I can clarify things and correct things if needed. But as far as completely reteaching things, I can't do it in 2 weeks. Sorry. So make sure you watch the videos, and then send me emails or talk to me after school if you have questions, and write them down so you don't forget.